Welcome to aminacademy.com. In fluid mechanics, let us discuss force exerted by a flowing fluid in a pipe bend, and we'll derive the equation for it. Look at this figure. Here the pipe bend as well, the radius is one end and other end is different. That means it's gradually decreasing, and from that water is flowing. Now in section 1, V1 equal velocity of flow. In section 1, P1 pressure intensity in section 1, A1 area of cross section, area of cross section of a pipe in section 1. Similarly, V1, V2, P2 and A2 for velocity, pressure and area of cross section in section 2. Corresponding values of section 2. Now, due to bend of the pipe, the water flow direction is changing with theta degree to the horizontal, like its flow is like. Due to that, the force is exerted. Here, this Fy, Fx. Here you can see P1 and A1. This is here P2 A2, P1 into A1 because force into pressure into area is force. Here P2 A2. Suppose this is a V2 velocity and this is a horizontal component V2 cos theta, here V1 sin theta, resolving the forces in horizontal and vertical direction. Here consider this figure. This, suppose this is theta, this component of this force is P2 A2 cos theta, and here P2 A2 sin theta. This is P2 A2. So the force P2 A2 is resolved in horizontal and vertical direction. Here this force Fx, this is force Fy. Here let Fx and Fy be the components of the forces exerted by the flowing fluid on the bend in X and Y, equal to Fx and Fy. Component of force, the force at bend are in X direction Fx and Y direction Fy. Here this component of force is in opposite direction of the flow of fluid. That is, you have to keep it minus F1 minus F2. Therefore, the momentum equation in x direction, therefore momentum equation in x direction is given by here this force is this direction P1A1 minus this P2 P2A2 cos theta. Here this is P1A1, this side is P2A2 cos theta. This is in this direction. Here that is P1A1 minus P2A2 cos theta minus Fx. That is resolving the forces in horizontal direction. That is P1A1 minus P2A2 cos theta and minus Fx. The net force acting in the momentum equation momentum force in opposite direction, that is minus Fx, which is equal mass per second of water flowing, mass into change in velocity into change in velocity. Here equal rho q. Q is the flow per second, flow volume per second. Rho is the density, that is mass per second, into change in velocity, which means final velocity minus initial velocity equal rho q. Here the final velocity in x direction is v2 cos theta. Here this v2 cos theta and v2 cos theta minus v1. Here suppose this initial velocity, this final velocity in therefore we can write P1A1 minus P2A2 cos theta minus Fx equal rho q v2 cos theta minus v1. From that we can get it Fx by collecting on side. Fx equal rho q v2 cos theta minus v1 v2 cos theta, then plus P1A1 minus P2A2 cos theta. This is force in x direction. Now similarly for in y direction, in y direction Here in vertical direction there is no force on the fluid because it is flowing horizontally. Therefore 0 minus P2 A2 sine theta, that is here P2 A2 sine theta, and minus Fy force in y direction minus Fy equal same rho q V2 sine theta minus 0. Here also V2 sine theta, this minus V2 sine theta. Here for initial velocity is 0 here. Then collecting one side, like Fy equal rho q minus V2 sine theta minus rho 2 A2 sine theta. This is equation 2. That is, here we got Fx and Fy. Therefore, there is now the resultant force suppose let it be Fr acting on bend is equal Fr equal square root of Fx square plus Fy square, and the angle made by the resultant force made by Fr with horizontal direction is given by tan theta equal Fy by Fr, that is here. Therefore, the angle made by the forces due to bend is theta can be calculated by using tan theta equal to Fy by Fr. So these are two results we obtained. We have done. Please subscribe our YouTube channel.